Hey guys, welcome to Digital Geometry. I'm going to try my best to explain things through this, post on Google Classroom and on my YouTube channel. So we've been working with angles and circles. We're going to continue doing that a little bit today. We're also going to talk about some random chord properties that are pretty helpful. So the first part of this lesson is more proof-based and the back is more numeric-based. For this first example, they're telling you that chords A, B, and C, D are parallel. So we know a chord is a segment within a circle. It's 2 points on the circle. If you have parallel lines, you guys are excellent at knowing alternate interior angles are congruent. So I wrote that down here. But then there's also something else going on. So what happens is, because angle 1 is an inscribed angle, the vertex is on the circle, it's half of the measure of A to C. I'm just going to mark that with a little, color green for St. Patrick's Day here. And angle 2 is also an inscribed angle. So it's half the measure of the arc it's across from. So the deal is, because these inscribed angles are congruent alternate interior angles, the arcs across from them have got to be congruent. So the way we write that up, and the property I really want you to take away from this is, if you have parallel chords, the arcs in between them are congruent. So we say the arcs that are intercepted. That doesn't mean the leftover arcs out here are equal. So A to B, I don't know if that's equal to C to D. I don't have enough evidence of that. So let's go to the next idea here. Now, what if I have congruent chords? This doesn't happen often. I'm going to show you a proof, but I'm going to outline what I mean by congruent chords. So C to D, that little chord there, and A to B are the ones I'm saying have to be the same length. Intuitively, this makes a lot of sense to students, but the property that I want to show you is, if these red chords are equal, the arc in between won't be the same length as the red, but this blue arc and this blue arc will be the same exact degree measure. They cut the same amount of the circle. In terms of a proof of that, I drew in some radii. So radius, 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 radius. We know those are all equal. They told us the red lengths are equal. So the triangles have to be congruent by side, side, side. And then you could say, these leftover angles are equal because they're corresponding parts, and that's down here under part B. And these angles happen to also be central angles, which we know are the same degree measure as the arcs they intercept, the arcs across from them. So these angles are equal. Those arcs across from them have to be the same amount. Again, the takeaway is, I don't need you to prove this every time, but if you have congruent chords, the arcs across from them will be equal. And the converse, the vice versa of that is also true. If the arcs are congruent, if you knew that to begin with, the chords that cut them would have to be equal. So I wrote that down here. Let's go to the back though. This is where we kind of get into the numbers, kind of more fun looking at some of the properties here. So with this first one, they had these markings like such. Okay, so 2 hashes. I'm not very good at freehanding this. So this is equal to this blue one, is equal to this blue one. So I know there are 360 degrees in a circle. So I divided that by 3. So now each one of these arcs has to be 120 degrees. So I filled in the diagram there. Then, using this new idea, if these arcs are all the same, any chord that runs along them that connects them, if you want to think of it like that, those have all got to be the same length. So nothing with angle measure, all about length once I get to these segments. So they told me this was 17, therefore that's 17, and that one is 17. Looking at the next example, so what did they start with? Looks like they started with this 56, so that's how many degrees are in that arc. They're telling you that this segment and this segment are congruent. Therefore, I can use my new idea that the arcs across from them, and again, I'm just using different colors to differentiate here, the arcs across from them are also congruent. I notice that this is the center of the circle. I'm not trying to trick you there. So this is a diameter. Therefore, this semicircle adds up to 180. So you can set that up algebraically. You could say x plus 56 is 180. You could have subtracted up the 56 from 180 and divided by 2. Either way, I know that these leftover green arcs, or the measure of arc x, is 62 degrees. And then going back to what we did a couple weeks ago, ooh, I like this purple one. So inscribed angle here, boom, that's half of the 62. Inscribed angle here, that's also half of the 62, so both 31. And if you really wanted to make some other conclusions, these lines would then have to be parallel. Let me erase everything. Okay, so a couple more examples here. Oops. So this example, this is a quick one. They're telling you have a diameter, cool, whatever. You have some parallel lines, nice. A to B, this arc is 80. We know this arc over here is 180. I'll write that in. Oh, there we go. So again, these aren't equal. Fine. However, what I want you to know is the arcs in between that are intercepted by the parallels, they're the same exact measure. So we took the 180, took out the 80 degrees, you're left with 100. So 100 divided by 2, this arc from A to C has got to be 50 degrees. Then the last example I want to show you, if I go all the way down here, drawing diagrams. This is tough. We're going to try our best with this as we do the digital classroom, but they're not giving you a diagram. You might have to redraw it. Don't get frustrated. Use your pencil. But they're telling you you have two secants that intersect outside of a circle. So the first thing is, what's a secant? Well, it's a segment. It's just a chord that's been extended. So it hits a circle twice and goes outside the circle. So I have two of those. They meet outside of the circle. I think secant, secant, same thing too, whatever gets in your head. They form an angle that's 38 degrees. I put my 38 degrees there. The smaller of the two arcs it intercepts. So if I were to outline this secant, I don't know the length of it. I don't know the length of this one, but that's okay. If I look in between, so the arc, the smaller arc it intercepts is 65. The larger arc, I don't know, so I'm going to leave that as my variable x, is what I want to find. So I'll remind you of what we did in class on Friday. You take the larger arc minus a smaller arc, divide by 2, and that now equals this random exterior angle that we don't have a name for. So in terms of solving this, a lot of you like to put this over 1, cross multiply. You would get x minus 65 equals 76. Add over the 65, and there's your larger arc. Remember, you can always do a quick check. Go back through and say, if this arc is 141 minus 65, divided by 2, I'll get 38. So that's all I have for you today. I will talk to you in Google Classroom.